Hello everyone, I'm Professor Harrison and welcome back to our module on statistical inference. Today we're going to be talking about the one sample t-test. This is the hypothesis test you use when you're comparing a sample mean to a known benchmark and the population standard deviation is unknown. In practice, the population standard deviation is almost never known, so this test ends up being a pretty standard tool for the kind of question that we're asking. We're following Bess. She's an investigative journalist on a cold case she can't let go. Today she's not investigating anyone else, she's actually defending herself. Her editor flagged her expense reimbursements and wants to know why her work lunches are running a little bit above the office guidelines. The office keeps their lunches at around $30 per person. Her last 16 submissions, however, averaged around $33, and her editor was not happy. She pulls up her case file. We've learned how to run a hypothesis test. We've built the full framework: a null hypothesis, a test statistic, critical values, and making decisions. We introduced it using z-tests, where the test statistic follows a standard normal distribution. But z-tests rest on a specific assumption. They require you to know the population standard deviation up front. In practice, you almost never have that. You have a sample. You estimate the standard deviation from the sample data that you're testing, and the moment that you do that, the distribution of the test statistic changes. When you estimate the population standard deviation from the sample, you introduce an extra layer of uncertainty. The sample standard deviation is a random variable. It varies from sample to sample, just like the sample mean does. That extra variability means the test statistic no longer follows the standard normal distribution. Instead, it follows the t-distribution. We already met the t-distribution when we built confidence intervals. It's bell-shaped and symmetric, but with heavier tails than the normal. Those heavier tails reflect the additional uncertainty. It's not just variability in the sample mean, there's additional variability from estimating the spread itself. And as the sample size grows, the estimated standard deviation becomes more precise and the tails lighten, and then the t-distribution approaches the standard normal. The relevant parameter for the t-distribution is the degrees of freedom. For a one-sample t-test, degrees of freedom equals n minus 1. We lose 1 degree of freedom because we used the data once already to compute the sample mean. That constraint limits the remaining independent variation available to estimate the spread. The t-statistic has the same structure as the z-statistic that you already know. It's the sample mean minus the null hypothesis value, divided by the standard error. The only difference is the standard error uses the sample standard deviation s rather than the population standard deviation. So the formula gives you the sample mean minus mu naught, all divided by s over the square root of n. Once you have the t-statistic, you compare its absolute value to the critical value from the t-distribution with n minus 1 degrees of freedom. Exceed the threshold and you reject. If you fall short, then you fail to reject. Going back to Bess, she has 16 reimbursement submissions. Her sample mean is $33 and her sample standard deviation is $8. The null hypothesis is that her true average work lunch costs $30. The alternative is two-tailed. She's not claiming a particular direction, she's just responding to a suggestion that something is off. The standard error is 8 divided by the square root of 16, which gives us 4, so the standard error is exactly 2. The t-statistic is 33 minus 30 divided by 2, so that's 3 divided by 2, or 1.5. The degrees of freedom here is 16 minus 1, which gives us 15. For a two-tailed test, at alpha equals 0.05 with 15 degrees of freedom, the critical value from the t-distribution is approximately 2.131. Her test statistic is 1.5, so it does not clear the threshold, and she fails to reject the null. The $3 gap between her mean and the $30 guideline sounds like it means nothing, but given the sample size and variability in the data, a gap that size ends up being exactly what you'd expect by chance, even if her true average were $30. The test is telling her editor that this result is not surprising, and that it falls well within the range of normal sampling variation. This is the real payoff of the t-tests, not just identifying what's significant, but protecting you from the very natural tendency to treat anything different or above 0 as meaningful. In her article, Bess explains this to her readers. The average was above 30. The test said that that kind of gap shows up all the time by chance, even when nothing is wrong. Being above the number and being significantly above the number are not the same thing. One interesting thing about this circumstance, however, is that Bess may or may not have been buying a candy bar on her way back from lunch every single day. That candy bar was worth about $3 and it might have had something to do with the increase in her prices. The good news for her is that her sample size was small, so in this circumstance there wasn't enough evidence to convict her of her candy bar crimes. So that's the one sample t-test. Use it when the population standard deviation is unknown and you're estimating it from the sample, which is almost always the case. The test statistic is the sample mean minus the null value divided by s over root n. It follows a t-distribution with n minus 1 degrees of freedom. Compare it to the critical value for your chosen alpha and apply the same decision rule that you already know. The only real difference from the z-test is that extra uncertainty from estimating the spread, and the t-distribution accounts for exactly that.